Okay. Good dear students, good morning to all of you. So today we will continue this subtopic of your center of mass, impulse. So impulse normally we are representing with symbol capital I. So first, what is the meaning of impulse? So in general definition, impulse is nothing, it is a change in momentum. It means, let for example, suppose a ball has been released from a certain height. At this time, this ball having velocity or u1 and its mass your m1. And we can write this time is your t is equal to t1. Okay? So it is coming down under force. That force can be said as a gravity. Somewhere here, its velocity or ut. Mass is the same. So time is your t. Okay? So it's the momentum we are changing. This point I can say initial point, initial momentum your m into u1, and this is the vector quantity momentum. So direction of initial momentum your downside, and here final momentum I can write, or momentum at time t2 m into u. Okay. So now this is a change in momentum. So impulse is nothing, it is simple change in momentum of a body in a particular interval of time. Okay? This is the basic definition of the impulse. Now, what is the cause of change in momentum? The momentum is changing is, see here, mass is your constant. Mass, we are not taking any variation in the mass. So what is changing here in fact? The velocity is changing. As we know, according to Newton's law, so whenever the velocity changes means it has some acceleration. The acceleration is there means some force is acting. So change in momentum is always because of the some force is acting. So that force can be either change the magnitude of the velocity, or can be change the direction of velocity, or it can change both. So it doesn't matter either magnitude changing, velocity changing, only we have to think about either velocity changing or not. Velocity is a vector quantity. If the magnitude changes, then also velocity changes. If direction changes, then also velocity changes. Or if both changes, then also velocity changes. Okay. So what is the cause of change in momentum? The cause of changing momentum here is the force. That force is nothing. It is the gravitational. It is the gravitational force acting in the downward direction. Okay. So first of all, we will define the momentum, impulse. So see, how can we write them? It is just one example I told you. From the impulse example, you can understand in a better way. See, impulse. Impulse of a body means impulse is nothing. It is the change in momentum of a body. Impulse acting on a body. Acting on a body or part is defined with the change in its momentum. Change in its momentum. Okay. So I can write here. So it can be written as, it can be written as I is equal to the final momentum minus initial momentum. Okay. Now, so this, as we know, this change in momentum because of which region? Because of the force. Here force is your gravity force, but in sometimes some other force may be there. So if I am generalizing here, so in general, see, in general, this change in momentum is because of the force, and in how much time interval? Between t1 to t2. So impulse is your in fact the product of the force and the time interval in which it has been changed, momentum has been changed. Impulse is equal to force into time interval in which momentum has been changed. Pi minus the initial. So I can write in general I is equal to F4 delta T is equal to your change in momentum delta T. This is the definition of your impulse. Fine. So impulse can be said, we can calculate either by changing the momentum of the body or by using this relation also. It means if force is acting on a body for a particular time interval delta t, so product of the force into time interval also give us the impulse, or it also changes the momentum of a body in that interval of time. Fine. So it's very simple definition here. Now here, as per the definition, we can say what are this SI unit, what is their dimension, what is their you can say this direction and all those things. First point I can write here, the direction of impulse is same as the direction of change in momentum, or the direction of impulse is the same as the force, direction of force which causes change in momentum. So direction of impulse is the same as direction of change in momentum. Change in momentum, direction of change in momentum, or direction of force which is responsible for change in momentum. Fine. Second point, it's SI unit. Direction SI unit of impulse is nothing. It is the SI unit of your momentum. Momentum SI unit, your momentum is your mass into velocity. Mass kg, velocity is meter per second. So SI unit of impulses is, see, there are two ways you can write. Impulse, force into time. Force means here Newton, time is second. Either you can write Newton second. The SI unit of impulse is Newton second, or impulse means change in momentum. Mass into velocity. Mass means your kg, meter per second. Third point we can write dimension of impulse. Dimension of impulse. See, dimension of impulse is your MLT minus 1. Okay, fine. Okay, next point here. There are 2 points we can say regarding impulse, or impulse we can categorize into 2 parts. One we can say uniform impulse, another we can say instantaneous impulse. Now, impulse can be categorized as, let first is your uniform impulse, and second we can say an instantaneous impulse. impulse. Okay. So first write up to here, then I will just differentiate what is the meaning of uniform impulse and what is the meaning of instantaneous impulse. Okay. Okay, now come to the difference between the uniform and instantaneous impulse. So uniform impulse means when the force acting uniformly, just like in this example here, the gravitational force is acting here uniformly. This force is not sudden force, continuously it is acting. Instantaneous impulse means when any force instantaneously act, suddenly act for a small interval of time. Okay, so I can say like that, when a momentum or impulse, when a momentum is changing because of the uniform force, then that impulse can be said as a uniform impulse. Or change in momentum is because of the uniform impulse. When a uniform force acting on a body continuously, force acting on a body continuously, when a uniform force acting on a body continuously for a long interval of time, okay. So change in momentum due to that force is called your uniform impulse. Then change in momentum due to that force, momentum due to that force called uniform impulse, because momentum changing uniformly. For example, first example, gravitational force. Okay, gravitational force give us which type of impulse? Uniform, because it is acting continuously. Gravitational force gives uniform impulse. Uniform impulse because see, here velocity I write to u1 and here velocity you can say u2. So in this, during this period, delta t, whatever change in momentum, okay, and this is because of the energy. Suppose next instant when you are taking, suppose u2 to u3 for same interval of time, then you will get the same amount of impulse because same speed changes, same velocity will change because force is your uniform, continuously. So in this case here, if I am talking about uniform impulse, the force acting uniformly, continuously, So from here to here net velocity or u1, and here velocity or u2, and this is under gravity only, no other force is there, and this here delta t is same. Again, if I am doing here velocity or u3, this is your u, mg is still acting here, mg acting here, and if this interval of time here delta t is same, then change velocity u3 to u2. Then change in velocity u3 to u2 and u2 to u1 in the same interval of time will be your same, because the acceleration here uniform. Or you can say if continuously force acting, uniform force acting, so that force is producing your uniform impulse. Similarly, so one example is, it means gravitational force always gives us uniform impulse. Similarly, another example is spring force. Another example, if I want to say here, is spring force. Spring force means here, suppose one body has been kept here, and so here, let here velocity of this is u1, and when the spring gets compressed here velocity or u2. So during from here to here, time interval delta t, the spring force is continuously acting here like this. So that spring force is not your acting instantaneously. It is not acting instantaneously. It is not acting for a small interval of time. It acted for a longer period of time. Okay. So that's why the spring force always gives us uniform impulse, because it is not acting here instantaneously. Since spring force never act instantaneously, never act instantaneously, it always gives us uniform impulse. So spring force always gives us uniform impulse. Fine. Now come to the instantaneous impulse. When sudden force acts for a very small interval of time. Okay, see. If I am talking about instantaneous impulse, okay, when a sudden force act for very small interval of time. So due to that force, change in momentum is called your instantaneous impulse. Due to that force, change in momentum called instantaneous impulse. Okay. For example, see how we can explain this examples. Okay, see this ball is coming down with under gravity. Okay, it has some velocity right now. Now it hits the ground. It is coming down under gravity with velocity right now. Here velocity u. When it reaches here, just it hit the ground. When it hit the ground, at this moment, how many forces acting? At this time, at the time of hitting, one force to already get gravitational force, another force normal force acting. Between mg and normal, which force your instantaneous? Can you tell me? Yes, normal force. Normal force your instantaneous. It acts only at the instant when the collision taking place, when the body was in contact with the ground, and that interval of time is very small. Okay, that interval of time is very small. Now see here, and let it hit the ground with velocity v1. Then what will happen? What will happen? After hitting, it will rebound, it will go up. After hitting, it will go up with some velocity of v2. See, very interesting point here. Although here mg is also acting, in the previous example, mg was changing the momentum in your downward direction. But now the momentum earlier was mg downward, now it is your upward. It means who is playing very major role in this case? Normal or mg? Normal force. Because normal force is too hard, it has changed the direction of the motion of the body. It means, what the conclusion we can say, that whenever any instantaneous impulse is there, or whenever any force acting for whenever a sudden force act for a very small interval of time, so impact of that force is too high as compared to your uniform force. So while you are solving the problem, the effect of instantaneous impulse you can say dominates over uniform impulse or uniform force. So in that case you can neglect the uniform force for that interval of time, for only that interval of time. Okay? So important thing is that when a sudden force acts for a very small interval of time, due to that force change in momentum called your instantaneous impulse. So here in this example here, normal force n is a instantaneous. Normal force is an instantaneous force, and it provides your instantaneous impulse. Because of that, instantaneous impulse will be there. The normal force n is your instantaneous force. Okay, normal force n is instantaneous force. The effect of this force is this force is too high as compared to any other uniform force, as compared to, in this case, gravitational force. Okay, so this is the meaning of the. It means normal force impact your very high as compared to gravitational force. So that normal force can be said as a impulsive force or instantaneous impulsive force. Okay. So a normal force called as an instantaneous impulsive force. While although both forces there, or mg is called a uniform impulsive force. So here normal force called instantaneous impulsive force, while gravitational force called force called uniform impulsive force. Uniform impulsive force. Okay? Understood the meaning of this? So, if we are talking about it means, and similarly, another example. Another example we can say here. Let this ball of mass is hanging there in proper inextensible string. Okay, and some other ball is coming here, and this ball you are hitting here. So when it was hanging, there are two forces was there. Tension and energy, both forces were your balance, means net force was your 0 because T is equal to your mg. It was at rest. When it hit, then what will happen? When this hit, what will happen? This ball will apply some force. In which direction? In this direction. Because this is the direction of motion of this ball. Now here, so this F force at which time only? At the time of your hitting. It was not acting earlier. And it will act for how much time? Just the time of collision only. Just at the time of only collision. So this F can be taken as a instantaneous force. And because of this F, what will happen further if you are looking up? Because of F, what will happen if I am looking the effect of this? This actor, so because of that, it has to move in this side. Because as per our Newton's second law, the net force is m into a, mass into acceleration. So net force T and mg was your balance. Net force of these two is 0. But what is the net force right now here? This F. So because of this, it has to go in that side. But very interesting point here. Suppose it is going and it will be here. Then the shape of, then the string will be like this. It means now the length of the string has to increase, but string your inextensible. Length of the string can't increase. What will happen? So as soon as this will try to go in that side, suddenly a jerk will develop on which part of the body? On the string. Because it will resist to move in that side. Because length of the string can't change. So the string will resist to move the block here in this side. Getting or not? This all thing happen instantaneously here. As soon as F active, it will have tendency to go in that side, but it cannot go in that side because length of the string cannot change it. So suddenly what will happen? Another force act on this block or in this body in which direction here? In the upward direction, which opposes the motion of this in this side. Clear? So that can be said as a T dash. Now it can't go in that side, then in which direction it can go? It can go only in which direction? Horizontal direction. In fact, right now, at this instant. After that, it may go like a which type of motion here? like a pendulum. Because in case of pendulum it is circular. In case of circle the length will not change. Understood? Getting the idea? So here there are in fact two types of impulsive force at the same time. Those are the instantaneous impulsive. So there is no effect of T and MT. What is the effect of only which two forces? T dash and F. Getting or wrong? So T dash is called your instantaneous impulse produced by the string on the envelope block or on the mass. F is the instantaneous impulse given by the colliding body. So here two types of instantaneous impulses there. The first, this type of analysis is very, very important. So what I told you here, normally gravitational force and spring force cannot give us instantaneous impulse, but other forces can give us instantaneous impulse. Getting or not? Because gravitational force always acts in the one direction, uniform, and spring force, spring cannot suddenly compress or suddenly elongate it. Slowly it will go. Spring will go slowly compressing or slowly elongation if has been pulled in that side. So spring force and gravitational force always give us uniform impulse. While sometimes tension can give us instantaneous impulse, sometimes colliding force can be said as a normal force, as in this chapter here collision, normal force is there, that can give us instantaneous impulse. So what we have to do, we have to see if the effect of instantaneous forces are too large or very high, it will dominate the effect of your uniform forces. So at the time of writing equation, I will tell you how to write the equation. At the time of writing equation, if both type of forces are there, instantaneous impulse and uniform impulse, then you can neglect the effect of uniform impulse. You can just simply write the effect of only instantaneous impulsive forces. Okay? So here in this question here, F is the normal contact force between the two ball. Here F and T dash are instantaneous impulsive force on ball. Okay? Understood? So this was the first our idea to differentiate uniform impulse and instantaneous impulse forces. Clear? Any doubt?
Spring force is not launching. Spring force is not launching.
Very good this time, but it is not acting for instant. Our idea of this, our aim is that either it is your acting for instant or for uniformly. Uniformly means for uniform time, for a longer period of time. Okay, for a longer period of time. I am not saying that it is constant or variable. I don't have to consider about that. There is no use here, no meaning of the uniform or. Main thing is we have to differentiate first which forces are acting for a longer period of time, means even beyond the collision, and which forces acting only for a very, very small interval of time, to check which will dominate at a particular instant, particular event. Okay. Okay, so see here. So for instantaneous impulse, we can make a diagram like this between force and time. See, instantaneous impulse means sudden force acting on This is the time interval of T1 and T2. Suddenly the force happened. Okay, a huge force, large force happened for time interval of T1 and T2. So area of F the graph, because impulse is the product of force into time. So area of force and time graph, this area, give us change in momentum or impulse. So as I told here earlier, I is equal to F delta T, which is delta P also. Okay. So area under curve and time axis. Time axis is this area. Give us impulse. Give us impulse. Okay. So main thing is the area of the force and time graph give us impulse. Okay. I think up to here, any doubt, any confusion? Now come to the next point. Next point here, impulse momentum equation. Impulse momentum equation. This relation further I can use in another form. See, as F is equal to dp by dt, rate of change of momentum. A force is responsible for change in momentum in dt time. So this I can write F dt is your d. This is nothing. Same. dp is change in momentum. F dt is this. Now integrate. When we are integrating here, dp, here I can write final momentum, initial momentum to final momentum, initial momentum to final momentum. This equation can be written as F dt, which is your final momentum minus, and this term is nothing, it is your impulse. Impulse is your force into time interval in which momentum is changing. The impulse is it is normally standard form of writing this equation. Okay? So this equation is called your impulse momentum equation, because impulse I, momentum is this. So in this coming chapter means impulse as well as collision. This is a very important equation, and if you are able to apply this equation, then all questions you can solve very simple, very easy. Very important. I is equal to your final momentum minus initial momentum. And remember, important point, everything is a vector quantity. So, momentum will change only in the direction of force, in the direction of force only. The change in momentum is in the direction of force. The force is responsible for change in momentum. Same thing here. As we have earlier studied, conservation of momentum. If force is not there, if F is 0, then what will happen? Impulse will be 0. Impulse 0 means final momentum minus initial momentum is equal to 0. The final momentum is equal to your initial momentum, that is called the conservation of momentum. That is called conservation of momentum. Okay, so conservation of momentum, from here we can also write. So this is a very key equation for solving all type of questions here related to impulse, collision. See, few problems we will discuss it. The application is very important. Okay, so note down here.